Hi, if you want to learn how to draw the mechanism for creating an anhydride, then you've come to the right place. The mechanism for synthesizing carboxylic acid anhydrides is going to be very similar to synthesizing a lot of different types of carboxylic acid derivatives. Many of them is going to come down to a reaction type called the nucleophilic acyl substitution. This reaction is covered more in detail in another video you can check out as needed. But a quick overview shows us that we have an acyl group, which is a carbonyl group with a leaving group attached to it, a nucleophile, and a nucleophile is going to attack a carbonyl carbon because it's slightly positive charge. That then breaks one of our bonds to our oxygens, and we result in our intermediate with a negatively charged oxygen. Now, at this step, you should always ask yourself if there's a good leaving group. Because if there is, we're going to reform the carbonyl carbon and kick it out. That brings us to the substitution part of the reaction and our products, which involve a nucleophile attached to the carbonyl carbon in place of the previous leaving group. So again, you'll see this reaction very commonly when it comes to carboxylic acids and their derivatives. Now let's focus more specifically on a reaction that makes carboxylic anhydrides. A very common way to do this involves an acyl halide and a carboxylate. To identify an acyl halide, you're looking for a carbonyl carbon bonded directly to a halogen. And then the carboxylate is going to be the deprotonated form of a carboxylic acid. So these are going to be your two major players in this reaction to form an anhydride. We're going to have our acyl halide with the carbonyl carbon with a slight positive charge. The carboxylate is going to attack being a nucleophile, and we're going to break a bond to that oxygen. That results in our intermediate, which is tetrahedral. And then once again, at this point, you want to ask yourself if you have a good leaving group. In this case, we do with that halogen. So we're going to reform that carbonyl bond. We're going to eliminate this leaving group, this halogen, and we're going to be left with an anhydride and then the halide. So again, this is an example of a nucleophilic acyl substitution. It's just specifically getting us an anhydride as a product. Now go ahead and get a little bit more practice. Draw out the mechanism for this reaction. You always want to find your nucleophile, your electrophile, and see if there's any leaving groups in there as well. So it looks like we have our acyl halide and our carboxylate, just like we had in that previous example, which means we have our nucleophile and we have our electrophile. And just like before, our nucleophile is going to attack your electrophilic carbonyl carbon. We're going to break that bond to that oxygen. We're going to get our intermediate with that negative charge on the oxygen. We always want to look for that leaving group. Here it is. We can break that thing off by bringing those electrons back down and reform that double bond, and that kicks out the bromine. And that's going to leave us with our anhydride as a product. Overall, if you're faced with reactions involving carboxylic acids and their derivatives, they're commonly going to come down to that nucleophilic acyl substitution. And a good place to start with that is to look for nucleophiles, electrophiles, and then consider if there's a leaving group.